Truly excited to be back again. I actually talk to you more about organic chemistry, which is the third level where we focused on particular transition metal complexes that are going to be constructed and being used to drive catalysis in various organic chemical reactions. So in our previous video we looked at palladium and we saw that palladium can actually interact with specific ligands, and we're able to establish the electron counting to help us to explain the stability of metal complexes. And on our video we actually kind of touched on the bond that is actually constructed between a specific metal and the ligand. Now in this video, really excited to actually say that we're going to dive more into the bonding in transition metal complex. So first off, there are actually three ways by which we can actually explore this particular statement. First one is actually noticing that we have the ligand which has a lone pair of electrons filled in the sp n orbital. So n meaning that we can have 1, 2, 3 in there, and these types of orbital will actually overlap with I would say vacant, take note, vacant metal dsp orbitals, and take note here that it could be a d orbital, a s orbital, or a p orbital. So an example of this is where we have a metal which is represented as M actually introducing an empty d or s or p orbital, and this will actually try to overlap in the right orientation. Take note of that, with a ligand of similar symmetry, and this is actually filled, and this is filled with lone pairs of electrons. So what that results in is the donation of electrons from the ligand over to the metal to generate a type of bond. And what is this type of bond called? Sigma complex, right there. So that's about it for the first part, where we saw a ligand, or we've seen a ligand with a filled sp orbital actually interacting with a metal. So let me just specify this to be a sp orbital, either n being 1 or 2 or 3. Now the next one in here is a case by which we actually have the bonding between a filled d orbital from a specific or any metal and that of a vacant ligand orbital of appropriate symmetry, like that of a pi star orbital specifically, is where we have antibonding in that particular orbital orientation in that particular compound. So that being said, we're going to dive into a case scenario where we have a metal which is actually expressed as M, but in this case it has, I would say, a lone pair, and on the other side we have a ligand which actually, I would say, is carbon monoxide, or I would say a carboxyl in a way. And what happens now is that this actually has a lone pair on the carbon and lone pair on the oxygen, which shows that the oxygen will have a positive charge and the carbon will have a negative charge. The overall on this particular ligand's charge is actually neutral, because this net charge is actually equals to 0. One part where the metal actually donates its, I would say, pi electrons to the ligand, while on the other side we have a case by which the ligand actually donates its lone pair of electrons to the metal to form a sigma donation from the ligand over to the metal. So let's look at these two scenarios and see which one is the more force or the more contributing factor to the overall formation of the bond. So what we realize is that from the first or the second part, which is the formation of the sigma donation, we actually have the metal orienting its orbital in such a way that it actually has a side attack with our ligand in here, where this ligand donates its own field orbital right here, and this field orbital is actually from the ligand is going to be, in this case, a sp, because it's coming from a triple bond right there. So this field sp orbital is going to overlap with a empty d orbital. An empty orbital is done in such a way that this is actually shaded and that is actually shaded in there, and this actually reveals that, hey, we have an electron donation that is actually going from the ligand over to the metal, because the ligand has electrons and is donating it to the metal. Now the other case scenario is the pi donation, and in this case we have the metal now orienting its orbital in, I would say, a different way. And what we notice now is that once this is shaded and that is shaded, we actually have this ligand having no other choice than to actually introduce its pi star, and this pi star actually shows that on this particular lobe is shaded, and on this other lobe to create a node is actually at the bottom shaded. So as a result of that, what we get is the formation of a bond right here and right there, and the metal here is known to have a filled d orbital, and this here, which is our ligand, has an empty pi star orbital, and this actually reveals that there is electron donation going from our metal over here to our ligand. So as a result of that, the better contribution of electrons to the formation of the bond is actually the second one, which is the pi donation, and this one here, which is the sigma donation, is not actually the high or the huge driving force for the formation of that particular bond. Now finally we have the third case where we have an alkane, and this alkane has, I'll say, double bond between carbons, and this is going to be interacting with a metal but sideways. So how is this actually established? There are actually two contributing factors that actually support this particular style, I would say, of orbital overlap that leads to the formation of a bond. One case is where we have a metal, and this metal actually brings out, I would say, its vacant metal orbital. So the MVO means the vacant metal orbital, and this is going to be contributed to the sandwich orbital, which is the pi orbital on this particular alkane. And what that results in is that we have the formation of a bond, and the formation of a bond is caused by the electron rich region on this particular ligand, which is the alkane pi, and that of the vacant metal orbital. So as a result, we have the electron donation going from the ligand over here to the metal, and this actually leads to the formation of a bond sideways. Now the other case in here we're going to look at is where the metal actually brings its d orbital, and the d orbital is going to at some point going to try and overlap now with the other part, which is a pi star, and this pi star actually shows that, hey, in here we have the lobe shaded here and this other side not shaded, so this leads to antibonding. And on the other side, which is a metal which is electron rich, in here we'll have here being shaded and there being shaded. As a result of this, we're going to have the formation of a bond right here and right there, coming from the ligand that it is electron poor due to the lack of electrons in there. So the contribution of both this particular case and that particular case, where this particular second case has the electron donation going from the metal to the ligand, and the first case where we have the ligand donating electron to the empty metal, results in the formation of a bond, which is actually shown as this, where the metal donates or forms a bond with the pi system between the carbons right there, and this results in the formation of our bond. So that's about it for this particular video, where we're able to explore all the 3 cases by which we can actually form a bond in a particular transition metal complex. First off, looking at a ligand that is electron rich interacting with a vacant metal, DSP. Second case is where we have a field D metal interacting with a ligand in the anti-bonding orbital style. And the final one is where we have a metal interacting with an alkane in a sideways way to actually result in the formation of a sideways bonding in there. So all the same, thanks for following me through this. Truly appreciate it. Hit a comment down below, let me hear your thoughts about this. By that way, I can talk to you all later. Stay smart and believe in yourselves.